Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to talk a little bit about how to calculate both electric fields and electric potential due to point charge configurations. So what we're going to do here is we're going to take a look at this charge distribution here. Let me chat about it a little bit here. I've made up a couple of charges that we're going to assume are positive in nature here. So we're going to call this one Q1, and this one Q2, and this one Q3, right? I've color-coded them. I don't mean to imply that, positive charge is somehow orange here. I just like to, I like the videos have a little bit of color. They make it more aesthetically pleasing. So whatever Q1 is, it's missing some electrons, giving it a net positive charge. Same thing with Q2. This animal right here has extra electrons, giving it a net negative charge. And what we're going to do here is we're going to calculate the electric field and electric potential here at the corner, which at the point here I'm going to call P. Now before we do, it's important to realize what these things are. So let's start with the electric field here. So the electric field is defined as force per unit charge. And it's real easy to rearrange this and see that the force on a charged particle is equal to charge times the electric field strength. So, why would we want to know the electric field here? So that if we did put a charge here of some value, we could calculate the force on it. Now, the electric field due to a point charge is equal to kq over r squared. Now this gives the magnitude of the field due to a point charge. The electric field points away from the charge creating it if the charge creating it is positive, and towards it if it's negative. So we'll go ahead and use this a little later in the video here to find the electric field at that point. Before we do that, however, let's talk about electric potential. Right? So electric potential is defined as potential energy per unit charge. It's real easy to show that, therefore, potential energy is equal to charge times electric potential. So why would we want to know the electric potential here? Well, so that if we did put a charge at this location, we would know its potential energy. All right, so let's go ahead and start looking at the calculations here. First of all, I want to move this. There we go, that's good enough. All right, so we'll start with this, the electric field. Now, electric fields are vector quantities. That means that we need to draw electric field vectors at this position here. So charge 1 is going to create an electric field here. That's going to be to the right. And I'm going to go ahead and call that, how about E1 here for the electric field due to charge 1. And its magnitude is going to be kq1 over this distance squared. This distance is labeled as a in my picture, so we'll put over a squared there. Let's do this one right here next. There's going to be an electric field here due to charge 3. Because charge 3 is negative, the field here will point down towards charge 3. The magnitude of that field is going to be kq3 over this distance squared. That's b squared. Let me comment a little bit about the relative magnitudes of these. In this problem that I've made up here, I don't have numerical values for charge 1 and charge 3, so there's really no way we can assess the relative lengths of those vectors. The intention of this video was not to do so. It's just to, given these generic charges, how do we draw the electric field vectors and do the electric field calculations, and also the electric potential calculations. All right, let's talk about the electric field at this position due to this charge. And actually, this is my labeling here. I'll move that over here. Again, that's point P. The electric field at this position due to this charge is going to be away from this charge, so it's going to look something like this. Let me call that one E2 for the field due to charge 2. And that's going to be in magnitude kq2 over this distance squared. Now, if you look at this triangle here, let me draw it in green here quick. The distance we need for charge 2 is this distance. That is the hypotenuse of this triangle. And I think I'll go ahead and just leave this triangle here for the problem. Here's an angle theta that we're going to need. And by Pythagorean theorem, this distance squared, I'll put r squared, is equal to a squared plus b squared, right? A squared plus b squared equals r squared. So for now, because I'm short on space here, I'm just going to put r squared in the bottom. But when I rewrite this later on, I'll go ahead and put a squared plus b squared. Now, there's my electric field vectors, and complete with magnitudes. And you'll notice the electric field vectors point away from the positive charges and towards the negative charges. All right. Let's see, I forgot to label that one as E3, field due to charge 3. Now, let's talk about adding these things. Here's what you can't do. You cannot just add this to this to this, right? Because what we'd be doing is adding magnitudes. You have to add these vectorially because the electric field is a vector concept. So let's do this. The net field, the net electric field, will have an x component in the I direction and a y component in the j direction. We're going to go ahead and add these, calling right positive and up positive. So this guy right here, hopefully I can get this in one line. So our net electric field is going to be, let's see, EX. Go ahead and use parentheses here. Now we get this by adding the x component of this to the x component of this to the x component of this guy. I'm going to go ahead and just go around this way. This guy's x component is 0. You can just leave it blank if you wish. This animal here is entirely in the x direction, so this represents the x component, kq1 over a squared. And then this guy here, the magnitude is kq2 over r squared. However, we want just the x component, so we have to multiply by the cosine of this angle. This angle and this angle are the same. I'm going to go ahead and write this over to the side. The cosine of the angle theta is equal to a over the square root of a squared plus b squared. That's because r here is equal to the square root a squared plus b squared. A is adjacent to theta. So for our cosine theta term, I'm going to go ahead and put a over square root a squared plus b squared. And you know, while I'm at it, I'm going to go ahead and replace this r now. Because remember that r squared is equal to a squared plus b squared. Let's go ahead and make that change. All right, so there's an expression that's going to represent the net x component of the electric field. 0 for this guy's x component, kq1 over a squared for this guy's x component, kq2 over r squared, right, which is equal to a squared plus b squared, times cosine theta, which is equal to a over square root a squared plus b squared. These are all positive because they all point to the right. All right, so I'll put I. I'm not sure I'm going to get this all in one line. I'm going to try, but I'm going to need a little more room. All right. Okay, next, j components. And again, I'll just start here and go around this way. All right, this guy's y component is down. So let's write that as minus kq3 over b squared. Now this minus sign is not directly because this is negative. It's because, right, as a result of this charge being negative, this vector pointed down. So this minus sign is because this vector is down and we're calling up positive. Moving on, this guy's y component is 0. And this guy's y component is going to be the magnitude, kq2 over a squared plus b squared. Now, again, I'm replacing the r squared with a squared plus b squared, times the sine of the angle theta. That's going to be the same as this angle theta, which is going to be b over r, or in other words, b over the square root of a squared plus b squared. J. So there's an expression for our electric field at this corner. Now, what can we do with this? Well, if we put some sort of charge there, and you'll notice that the force on a charged particle is charge times electric field. So basically, if I put a charge there and I multiply that charge throughout this, we would have an expression for the net force on that particle. All right, remember, electric field is a vector concept, so it has to be treated as such. All right, let's talk electric potential. So the electric potential at this location, I'm just going to go around this way. Now, electric potential is not a vector concept, right? It comes from ideas of energy. It's a scalar concept, so you don't need to worry about directions. The electric potential at this location due to this charge, right? Well, let me go back here and I'll write this over in the corner. The electric potential due to a point charge is kq over r. R being the distance from whatever spot you're calculating the potential to the charge. So the electric potential here due to this charge is going to be kq1 over this distance, which I've called A. Now this will be positive because charge 1 is positive. All right, this guy. The electric potential at this location due to charge 2 is going to be kq2 over this distance. And why don't we write that square root of a squared plus b squared. And then the electric potential at this location due to this charge is going to be K times Q3. Now, this charge is in fact negative. Let's, if Q3 is a negative number, we don't really need to put a sign on it. Let me just do this for now. KQ3 over this distance B. And let's handle the minus sign like this. Let's say that this is a magnitude. Let's say this. Charge 3 is some negative number. If you did put that negative number there, this term will come out negative, in fact. The other thing we do is just supply the minus sign and call this a positive value. That doesn't really matter, whichever one floats your boat. But it is important to realize that electric potential around a point charge carries the sign of the charge creating it. So the electric potential here due to this charge is positive. The electric potential here due to this charge is positive, and the electric potential here due to this charge is negative. So I'll just put here a little reminder where charge 3 is some negative number. And again, if you put that value in, that would make this expression negative. So anyway, the point of this video is, one, to kind of review a little bit about electric fields. And again, this is how the electric field is defined. And what do we use it for? Primarily for calculating forces on charged particles. And 2, to review a little bit about electric potential. Right, here's how electric potential is defined and what would we use it for? Well, a lot of times to calculate potential energy terms if I put a charged particle here. And then electric fields are vector quantities, so you always start by drawing those electric field vectors towards negative charges, away from positive charges. In order to add them, you need the magnitude of each electric field vector. Each one of these, because these are point charges, is a kq over r squared term. And then they have to be added vectorially, which means you need to take direction into account, and that's what this line does for us. So hope this video helps demonstrate how to calculate electric field and electric potentials. Have a great day.